Alright, so... Alright, we're recording again, so let's see, we got sound? Okay, we're good. I guess I'll keep that open. Didn't think anyone was gonna send me messages in chat. Okay, so... Actually, I kinda need... Where can I put this? Let's try to organize our screens for a second. Yeah, that's good enough for now. I mean, if something happens there, I'll be able to see it, and that's good enough. Okay. So we're just going to try to figure out how to add some kind of like sub-pixel, well, not sub-pixel geometry, but some sub-voxel geometry, right? So for each one of these voxels, with the gradation here. So this is a voxel, right here is a voxel, right here is a voxel. We want to kind of like carve into these voxels and give them some type of preset shape so that we can build some type of interesting geometry with it, right? Because right now we are going to be limited to just building with blocks if we keep it like this. And I'm going to use this engine as something to create patent render drawings for some patents I'm working on. And I, believe it or not, I have some shapes besides squares in those blueprints. So I need to figure out how to get like circles. Well, actually, I just probably need circles and it'll be good. But we'll try to get like auto tiling in here, and we'll try to get other shapes. And the first way I think we could try to get some geometry in here is we can take cross sections on or let's say projections on the X, Y, and Z planes of a voxel, and we can project those three planes together to create a 3D kind of volume for the voxel. So kind of like a hackish Boolean intersection using bitmaps. So the first thing we should probably do is... yeah, I think that's the first thing we should do. And we should think about, well, what's the best test shape we can use for that? And I think the best test shape for that might be something that is fractal based, right? Where we kind of have this base shape of like a Menger sponge. I don't know if I'm pronouncing that name correctly, but maybe we can create some projections on the X, Y, and Z plane for our voxel data to kind of create this shape within a single voxel. So the shape you're seeing right now, we can create in a single voxel. So let's give that a shot. I am getting kind of tired, so let's think about... there's a lot of ways we can approach this, but I guess the first thing is we just need the data, right? I don't know exactly what we're going to do with the data, but we definitely need the data. Now the thing is that we've kind of set up this engine to where the number of pixels in a single voxel is this variable thing here, right? So how are we going to rectify that with some type of geometric projection that is on the X, Y, and Z plane of a single voxel? How are we going to do that? And I'm thinking we just create some type of default bitmap, and we can just do like a bilinear sampling, right? Like if the bitmap we create for our projections is too small of a resolution, well, that's okay. That means that, you know, there'll be 4 pixels with the same exact data in them rather than just 1 pixel. That wasn't the best explanation. So let's just get into it. I don't know where we're gonna put this. We got a lot of stuff. Ray marching and voxel constants. So let's say let's make a subsection, right? So let's create a subsection called well, actually, we don't really have room for a subsection. Voxel projection. I don't know a better word for this. Voxel projection geometry? Something like that. And we'll use, that's a decent name, I think. We'll just roll with it, you know? Okay, so in here, we need some type of test value. So let's get to sketching really quick and think about what we could do to get something that kind of like is going to give us something good. Okay, so let's move over to the camera really quick and try to sketch something out here. Okay, first of all, are we right side up? So let me just... Okay, so we're right side up, and let's say that we have 3 projections that are just this. It's just this shape, right? It's just a 3x3 area with the center missing, right? And we're gonna project that onto a cube, but we're gonna project it onto all of the faces, right? So we have a X face, a Z face, and a Y face, or XYZ faces, right? One face per axis that the voxel is normal to. So this is normal to the Z-axis. This is normal to the Y-axis, I believe. And this is normal to the X-axis, right? These 3 planes here. So we're going to take them and we're going to project this shape onto it. So we're going to take this shape and we're going to project this onto all of the faces and create like a Boolean geometry from that. So what will that look like? I have no clue, and we're just going to kind of hackishly sketch it out and just take a guess at what that probably looks like, and I'm probably going to be wrong, but let's just do it, right? So we're gonna it doesn't have to be completely accurate. We just need a really rough idea of what's going to happen here. So we know that if we do this and we project the solid geometry this way, that it's just going to create walls. Actually, yeah, and this is going to go down like that. Yeah, so you know what? If I do a front view of this, since I'm horrible at drawing, so let's take this front view and think about the projections, right? It's going to, let's do some dotted lines and some dotted lines. So it's basically going to be, yeah, so it'll actually create like this shape here that we have on the monitor. We can create that shape in a single voxel by just projecting this kind of 3x3 bitmap onto all 3 faces of this cube that represents 1 voxel, and we can get kind of like this kind of shape. And there will be a gap in the middle, and it will just be kind of like this table kind of shape. Now, if we want it like thinner, you know, because maybe we want something where we use a shape more like, if we use 1, 2, 3, 4, 5, 6. So let's say we use 6 by 6 pixels to define our geometry. If we use 6 by 6 pixels to define our geometry, we can get a bigger gap in the middle. And I actually think a bigger gap would be nice so that we can kind of test out what's going on. But if we use this projection on all three of these faces, then we'll get something more like hold on. So then we can get something more like this, right? So where it's just like, right, it's just kind of like this frame. It's just this frame kind of shape, right? And that's all it is, right? It's just a really simple frame, and we just get it from, oops, we just get this frame shape by taking this one bitmap and projecting it on each surface, right? On each the z-plane, the y-plane, and the x-plane of the voxel, we just project this shape into each of those planes and use it as a intersection. Does that make sense, though? Because if this is... this is actually more subtractive geometry, isn't it? Yeah, because if we project this, if we do a Boolean, an additive Boolean with this shape, we're not going to get this. I think we'd actually get a, we would get a, what do you call it? A cavity. I don't know what the word is for it. So if we do this and we do it additively, we're not going to get this. Actually, what we would get is we would get, like, if we do the first projection, if we do one projection like this, we're going to get just like this, we're going to get like a box with a hole on each side, right? Like this, like holes on both sides, right? And then if we project this shape into it, well, this side is already closed, but if we project this, the shape onto this side, it's going to close off the top here, right? And then the third projection here, the third projection on this side, doesn't actually add anything new, I don't believe it, because everything has been closed off, and it's the geometry this projection adds by going into the shape that we've Booleaned together. It only goes over areas that have already been filled. So this would be if we took the geometry and we inverted it, and then we used it subtractively, then that is how we get it. So I think that because I initially thought of this shape, I think we should have an option to where we can use the side, we can apply the geometry subtractively or additively, right? And I don't know if it should be like everything should be subtractive, or like if we want to like selectively, some are subtractive and some are additive. Well, let's think about that. So if we're going to use this subtractively, we're going to start off with a cube, and we're going to invert this. So we're going to take this shape here, and we're going to convert it into 1, 2, 3, 4, 5, 6. We're going to take this shape, and we're going to flip the bits on this shape, right? So we're going to turn that shape in that bitmap into this, right? So we just invert it. We're going to invert the bits, and then we're going to use this projection to project into a solid cube, and then subtract the matter that it hits, or the pixels that it hits, right? Or the surfaces, or any of the volume that this projection hits by projecting onto the x, y, and z planes of the voxel. It will subtract that geometry, and we'll end up with this frame shape. So let's keep our source data as a positive, and then we'll use the positive for creating, God, what are these shapes called? Okay, I have to look this up because it's kind of annoying me. So let's go back to the camera, or not the camera, but let's go back here, and I'm gonna look this up. It's not a scaffold, so it's not called the scaffold shape. It's hollow. It's a hollow shape, right? It's a hollow shape, and there's a word for a hollow shape, and I don't know what it's called. So let's find what you call a hollow shape. It's called like a what do you call a hollow shape, right? Okay, so what do you call a hollow shape? I know there's a word for this. I guess we could just look at this and see if there's a mathematical definition. Well, let's, oh, manifold. I think it's called manifold. Cavity shape. I think it's called a manifold. Manifold shape geometry. And that might not be correct. I think a manifold might just mean, like when you were trying to print stuff. I know that, let's close. Oh boy, man, they're really... in mathematics, let's see. In mathematics, a manifold is a topological space that locally resembles Euclidean space near each point. More precisely, an n-dimensional manifold, or n-manifold for short, is a topological space with the property that each point has a neighborhood that is homeomorphic to the Euclidean space of dimension n. So, you know what? Don't know what homeomorphic means. We could go down a rabbit hole if we try to dig too deep here. One-dimensional manifolds include lines and circles, but not figure eights, because no neighborhood... yeah, let's do SDF hollow shape. Because I think that if we look up hollow... am I not spelling hollow correct? I don't know how to spell hollow, do I? So let's see if bounding box exact... And this is actually the kind of shape we're going to make. But we're going to use kind of these projections to make it. So this is elongation. Ah, wait, onion? Onion isn't quite... So it's not quite an onion, right? Because we're not going to give it a whole bunch of layers. We just want, like, one, onion is the closest, but that's not really what we want. So, try SDF onion. So let's kind of keep on looking this up. So SDF onion, and SDF onion. Okay. With that, let's just put this in our reference as SDF onion. And actually, use SDF onion URL. Search for onion. That's kind of convoluted, but that'll be a way to make sure I can get back there, right? So SDF onion URL, SDF onion URL. I'll paste that there. Okay. let's kind of keep on, let's just see if maybe in this shader toy example that maybe there's some more information. Carving interiors of shape. Shells. I think it's called a shell. Onion. You create onions, shells. Okay, so let's actually look up SDF shell. I think that might actually be what it's called. SD signed distance function shell. And let's look for some images because I know what shape I'm looking for, and let's see if we can find shelled volume SDF. Wait. Oh, hey, hold on. That looks about right. Understanding the basics of B-reps and implicits. Yeah, so I mean, this says... yeah, so I think it's shell, but, shell operation topology. Let's try that. And if we look at, yeah, I think it's called a shell. Let's go on www.shadertoy.com and let's see if we can Google not Google, but SDF shell. If we do SDF shell, do we find what we're looking for, right? Because I think that is, let's pause this. I think that's what we're looking for. No shell, no, let's just try shell, right? And see if we can find the actual shell operation rather than just see shells. This is just going to crash on me, so that might not be good if, you know, OBS is using... yeah, you know, we're just going to close this before it creates a problem for us. So, shell manifold? It might be shell manifold, maybe? Yeah, but I think the word is shell. Shell is my best guess right now. Or maybe the word is shell? So I think the word might be shell, but I'm not sure. Shell shape. Shape. So I don't know if that's correct, but we're just gonna go with it. I think that a hollow manifold is called a shell, and I could be wrong. So we got this voxel projection geometry. We've kind of thought about what that geometry needs to look like, and we can kind of borrow from here, and we know we should just take that. And in here, let's just, U32, I don't know what to call this. Let's just call it, SDF, projection. 1, right? We'll just call it SDF projection 1. And it's going to be a two-dimensional map, and I think 8 by 8 will just be fine, so 8 times 8. And the reason I think 8 by 8 is fine is because I did the graph paper drawing as a 6 by 6. but we might want define underscore as a U32 0, and then we'll define X as a U32 1, right? And so we'll just keep the defines really simple for now. The values are either on or off, and no weird in-between values for now. That could change later, but for now we'll keep it as simple as possible. And it's going to be 8 by 8, so we need 2, 3, 4, 5, 6, 7, 8, and then 4, and then duplicate that, and then get rid of the last semicolon. No semicolon. Oh, sorry, no comma. Last. I don't seem to know the difference between a semicolon and a colon, so no comma on the last one. And we have this 8 by 8 grid. Let's make sure that let's just do 8 by 8 equals 8 by 8. And let's just label this, right? So let's put some comments in here that can accurately label what we're looking at. And actually, let's use 1, 2, 3, 4, 5, 6, 7, and 8. And this is not the actual index value, right? Because this is actually, the first pixel is going to be pixel 0, 0. The numbers we are laying down right now are just checksums to make sure that we don't accidentally put the wrong amount of data in here, right? And I don't know how we're going to do that. I guess we can just no comma last. That's fine. 2, 3, 4, 5, 6, and 7. Okay, so we got a nice little template for our SDF projection. SDF projection shape number 1, right? Okay. And in here, let's just create that shape that we wanted to create, right? So this is our, this will create a cube shell, or a kind of like a, I don't know if you would call it a tesseract shape. I guess a 3D tesseract rather than a 4D tesseract. But if we invert this geometry and then use it as a subtractive projection on a cube, it'll create like a three-dimensional tesseract. If we take an empty space and we additively project this, then it'll create a shell shape. So I think that's how we're going to define our Boolean operations. When applied additively as a projection into empty space creates a cubic shell. When bits are inverted and applied subtractively to a And let's make sure that tesseract is the right word. So 3D tesseract. Like, tesseract actually might mean... I don't know if tesseract actually means that it needs to be a hypercube, or if... Yeah, because this is a tesseract right here, right? This thing is a tesseract. So 3D tesseract is kind of like not really what we're talking about. So we're not really talking about a cube, we're just talking about like a frame. So we're not really talking about a tesseract. Whatever, you know what? We're just gonna go with it. You know why? Because I don't have a better word for this, so let's just stick with that, right? Okay. So 1, 2, 3, and 1, 2, 3, or 1, 2. There we go. Okay, so now that we have that kind of stubbed in and we have that data, we can make sure that the that this is actually going to compile, like we didn't make any stupid mistakes. And I'm surprised, but we didn't. So we didn't make any mistakes. That still looks correct. Let's think about what's next. Like, what operations are next for this? We need some type of sampling function where we need to be able to map tile values to these projections. And so this is projection 1. So I think the easiest thing to do is projection 1 maps to the tile value 1, right? Simple like that, right? And then we need to just know the maximum number of projections. So what we'll do is... do we want to make that... yeah, we'll make it 1 based, right? Because 0 is often going to be empty space. Yeah, we might as well treat 0 kind of special. We can backtrack on that later, I guess. So yeah, well, we can backtrack on that later if that doesn't work out for us. So what is the max value for our projection? Is it like SDF projection max, or is it max index, or is it number, right? Number of projections. I think max kind of makes more sense. And we can define that, right? So we'll do define and that's equal to 1. And this is a so I'm going to do something kind of hackish. I'm going to put it right here. No, that's not good. Well, so here's my thought. My thought is we define it like this, and then when we want to use it again, we'll just undefine it and redefine it, right? So if we make another projection, let's just make one more projection so I can show you kind of like what I mean. And let's put the these defines, let's put them right here, because they're kind of like for this section. And let's say we add one more projection. So let's take this geometry here, and let's add one more projection. And we don't know what this projection does, so let's just remove that. And let's make it something else. Let's make it a... what other type of interesting shape can we get from just projecting these 3 planes? We could just make a cross, right? That could be interesting. Or we could just start doodling, right? And we could just see what happens as we kind of like just do stuff, right? So let's take... what would be interesting? What would give us something that would give us some feedback? So what would happen if we did kind of like the same thing, but instead of like projecting this way, we projected this kind of shape, right? So this would create, first we project down onto the Z and we create these pillars. And then when we project on this side over here on the Y face, the pillars get intersected, and that creates like a little cross here, across here, and then over here, from here to here, by projecting, we get O. So we get a cross, across, and a O. Okay. So I think that'll just. I think that this will just create like this another kind of tesseract kind of shape, but it will be. But it'll just be more dense, I think. I think that doesn't really give us anything that interesting. We could be asymmetrical about this, right? We could try. So I like where that could go. What if we just did this, and then the actual rotation of. Right, now the actual rotation matters, right? So how this, right, this we won't really know how it's being rotated around to create those projections, but we'll well, let's before we try to get interesting, let's get to just shapes and things that we can kind of just comprehend, right? So I think what would be easy to comprehend is just this, right? And yeah, right, because this will just intersect to make like a very tiny where the voxel should be, we'll just have a very tiny cube, because this is the only space that'll be filled up in the voxel, and that's only if it's going to be additive. 1, 2, 3, 1, 2, 3, 1, 2, 3, yeah. So yeah, we should try that. So so we actually do know what the shape here should be, and so additive. So now that we know kind of like that we're projecting in an additive and a subtractive way, we don't have to be so verbose. We can say that additive yields a small cube where voxel should be. Okay, and then subtractive yields a very thick shell. I don't have any better words for it. A very thick shelled shape. So if we do it additively, we get a very small cube in a voxel cell, and if we do it subtractively, we get a very thick shelled shape. Or do we? Because doesn't this create our shell? Oh no, this creates a shell if it's additive, right? Yeah, so additively this creates a shell with a very large void, and subtractively it creates that 3D tesseract, And then this will create if it's additive, it's going to create a really small cube, and if we use this subtractively, it's going to create a very thick shelled shape. Okay, so I'm kind of happy with that. I think that 2 pieces of data is good to work with. And so what I was thinking about, now that we have this, is when we add a new element, we could potentially do it like this. We could do... we could add a 2 like that, and then we could do this. We could just do undef SDF Pro Max, like that. Right, so we just redefine it. Or is that just asking for a world of hurt? Yeah, I think that's asking for a world of hurt. I get why I would do it that way, but then, like, there's this asymmetry where there's no undef on here, and yeah, I'm not buying that that's a good idea. So let's get rid of that, and hashtag SDF Pro Max is used here. By Okay, so let's just make a little note of the fact that SDF Pro Max is kind of like is here, right? So that way we can take this and we can actually put it in. If it's indented here, it kind of feels like something that should be undefined after we leave the section. It just seems like a really bad place for it, even though that's kind of like it's by the data itself, but I feel like it should be kind of like a more top-level thing where we kind of like put it up here somewhere. So we have like a configuration section, we have camera settings, projection geometry settings. So this is the new section, we'll call it that. We only have this thing right here. That's fine. And really this should be, if we want to be consistent with the way we've been kind of subdividing sections, a main section should be equal signs, but then subsections should have like thinner lines. We need like a line hierarchy. Because, right, this is me using kind of my art school training to look at that skilled way I'm drawing those dashes. There we go. Okay, so camera settings and projection geometry settings. So the total number of projection bitmaps used to create subvoxel geometry, and okay, so kind of typed up a nice little summary there. Might want to make a little space between that just so that we can see the comment and then see the value, just because with the way I've colored this, just it doesn't really stand out unless we kind of like make that visual space between that. So yeah, the total number of projection bitmaps used to create subvoxel geometry. 0 is currently not used because that will be the empty space tile. Thus, SDF Pro Max can be seen as the maximum inclusive index. If the tile value is if okay. So interesting thing we could do is we could make like tiles that are like negative be subtractive geometry, and then positives could be additive geometry. But the thing is we have already decided that we really want to stay away from signed integers, because eventually we're going to want to pack this data into a tile map that's using unsigned integers, right? And the reason for that is, let's say we just have a bitmap that's on our hard disk, and the bitmap is just pixel values that are unsigned integers, right? It has red, green, blue, and alpha, and those are 4 bytes, 32 bits. And the range for every single byte is 0 to 255, unsigned. So all that math for a bitmap and a bitmap's pixel values, it's all unsigned numbers. And so if we want to wrap our head around how the data goes from a bitmap onto a texture on the GPU and how we interpret those pixels into tile values, it would just be a lot easier if those values are all unsigned integers. So we're going to, so even though it might be kind of tempting to be like, man, we could make our tiles, signed values, and then, if it's a +2, it's additive, booleans, and if it's negative, then it's like a negative boolean. I think I'm going to stay away from that, and the way we might want to do it for now is we might just want to hard code some type of setting on each one of these projections. So SDF projection 1, so we could do, so let's just get rid of this. Let's first of all, we didn't even name that comment correctly, and this needs to be a 2. And let's change the formatting here a little bit, and let's do define SDF Pro 001 and TYP, and we'll do SDF Pro TYP additive. Right, so we'll have like we'll just hard code this as this shape here is going to be an additive projection, right? So we're just going to, it's kind of hackish, it's kind of ugly, but let's just get something that works. And I know it can be kind of tempting to be like, oh, we can do this, we can do that, let's add all of that flexibility. But with all of that extra flexibility means extra abstractions and extra complexity. So let's not get ahead of ourselves and try to make this more complicated than it needs to be. So we'll just say that we have just this constant for this projection, and we'll say that this is actually, this one should be additive, and then this one we want the kind of 3D tesseract. And let's look at our note. We see that we're just going to get a shell shape if we use additive, but in our notes, if we use the subtractive volume, we're going to end up with that tesseract shape. So for that, we know that we want this one to be subtractive, right? So we have two little bitmaps that we can use to construct some three-dimensional voxel geometry by projecting on the X, Y, and Z planes. And we can test one of these as additive geometry and one of them as subtractive geometry, and just see if we, can get that working, right? So before we get any fancier than this, we just want to get this initial data set to actually work. So let's take these constants here, and let's go up to where we used SDF Pro Max, and let's put that in our settings under the projection geometry settings. So we will do define, and what the value is, it doesn't really matter. It's kind of arbitrary, and actually, since it is kind of arbitrary, we can do something like define, right? It doesn't matter what it is, unless it was in some type of jump table or some type of lookup table where it's actually like going to go into like an allocated array. Then we wouldn't want 777, because then if this was going to be an entry within an array to create a jump table, then we would need, at least 778 slots, and some of those slots could be empty, right? So let's, but since I'm not going to do a jump table, we can use a large arbitrary number, and I am actually going to intentionally avoid using the value 0 for either one of these. And the reason why I avoid 0 for enumeration style values is because 0 could easily be the result of calocking memory, like 0 initializing a variable and then just forgetting to actually give it a meaningful value, right? So as a good habit in how I write my C code, I'm going to make sure that I avoid the value 0. So 0 will usually be indicative of a error if it's an enum. So it's usually like a forgot to initialize error if I see a 0 and a enum value. Okay, so now that we have that, I think all of our values are kind of like stubbed in. And we need to make sure that we didn't make any syntax errors, because I'm really good at making mistakes. So let's go to our shader code and just give that a run. And okay, well, wow, I guess, it's weird because I'm feeling kind of tired, but I haven't made any stupid mistakes yet. I mean, I have, but it's been a while since I made a stupid mistake. So with this, the next thing is we need some type of function that will take a X, Y, and Z pixel location within a voxel and figure out if the if the pixel within the voxel is on or off, right? Is it does matter actually exist in the voxel within that specific spot? And I'm not sure where we're going to put that function yet. I know it's going to be probably called by like SDF ray march into voxel. So let's look at SDF ray march into voxel. So I think it's SDF ray march into voxel. I'm not sure exactly what it's called, or it's not called that at all. So let's just say ray march. Look for the ray march value and see if we can find. Or maybe it was called like march into voxel. Okay, SDF march into voxel, right? So this is just kind of stubbed, is stubbed in here. And Right now, it just is returning. It's just returning 1 for telling me that we need to exit. Like, we've ray-marched for far enough, and now we need to exit. And let's figure out... so somewhere in this code... Somewhere in this code... So, somewhere in this code, we need to call something like SDF sample projection geometry. Something like sample projection geometry, and then that's going to take a... that's going to take like a tile X, tile Y, tile Z. Well, not tile, sorry. Tile would be the voxel, right? So our voxel map is just going to be a tile map abstraction, and we've just added another axis, right? So if you're familiar with a two-dimensional tile map, that's how we're doing this. So to me, in my terminology, how I am creating voxels, voxels are just three-dimensional tiles. And therefore, the voxels themselves have pixels. So you might be used to the analogy of a voxel just being a volumetric pixel. And that's not how I'm doing it. I'm actually saying that a voxel is a three-dimensional tile. So with that, how should we do this? We could give it a tile X, tile Y, tile Z value, and then well, the simplest way to sample the projection geometry, I guess, would be just give it the tile index, right? Because then we don't have to... From the tile index, we can... like, how much stuff do we want to re-look up, and how much stuff do we just want to pass right in, right? Because if we really wanted to be lazy, we could just say vox, we could just pass our vox00 object. And this voxel object is like a voxel container that, well, hey, look, it's right already up here. It contains like all the information about the current voxel that was hit, right? The tile XYZ location, pixel locations, all that stuff. It has lots of information. However, that's kind of wasteful because remember, we cannot pass anything by pointer in a GLSL shader. Everything is passed by value. And this vox object is pretty big. And so we might want to avoid kind of like wastefully passing this object around when we don't need all of that data in there, right? The only thing we really need is the 3D location of the pixel within the voxel, the local coordinate of the pixel within the voxel, which is a three-dimensional coordinate. However, we can use a one-dimensional index to locate that, so all of our data is stored in one-dimensional arrays, right? So even if it's three-dimensional information, we store it in a three-dimensional array. So we can pass like a index X, an index Y, and index Z, or we could just pass a index value, and then this index value, we can do some math on it to figure out the X, Y, and Z. And the reason why we might want to do it that way is because then it's less load on this function call, because it's just one variable instead of three. But what we save in using less memory, we lose in having to recalculate X, Y, and Z once we enter the function. And the thing is that without doing any profiling, it's kind of hard to know what the best way to go is, right? Passing an index is probably going to be more error-prone than passing X, Y, and Z, because that means that you have to correctly convert x, y, and z coordinates into an index before you pass it into the function, and then you have to successfully do the inverse of that math to unpack the x, y, and z from the index that was passed in. So it's much more error-prone to do it that way. However, I think that's the way I want to do it. So I'm thinking we just need the voxel value and the well, actually, we need the tile value. So it's the voxel tile value. So we'll call it a tile value like that, unless we have yeah, we'll call it tile value, and we need tile value, and then we need the tile, and then we need the tile value, and then we need the pixel D3D for index 3D. Now the question is, which piece of information should be first, which should be second? I know that that's like really pedantic, where it's like, why the hell does it matter? But we really should think about it. One rule would be general to specific, and I would say that the tile value is more general than the pixel, right? Because pixels are inside of the tiles, right? Because this tile, by tile I mean a voxel, right? Because our voxels are three-dimensional tiles, and within a tile is composed of pixels. So I would say this follows the general to specific pattern that I usually like to use. Would there be any reason for doing it the other way around? Now, I think that makes sense. So it makes sense to do it in this order. So this is kind of the way we want to do it. And I don't know where we're going to call this. So what we'll do is, you know, if some condition I don't know yet. So if some condition I don't know yet, then we do this thing here, and it should just give us back a unsigned integer value that is either a 0 or a 1. And we probably can get... I don't know if it would be any useful to... I don't really think it's useful to say that the value should be a byte rather than a unsigned integer 32-bit, because sometimes, because with the way the GPU works, it's probably just designed to work super efficiently by passing around 32-bit values, and trying to make the values smaller to save memory probably will not actually add any performance. It'll just be like, here's some space you could have used that you get for free that you're not using. So same thing with, like, if you've ever tried to do like a RGB texture, don't try to do that, because internally your GPU is using RGBA, and using a RGB texture because you want to like save space or something, that it's not really doing that. Internally it's still using RGBA, and you're just wasting a whole channel. So just use that channel you get for free for something. Now that's a big, broad, sweeping statement. It's probably not always true, but as a general rule of thumb, that's probably true. So yeah, I think I like this, and we can make a little comment here. Tile slash voxel value slash type. So when I put things in square brackets, what I mean is that these are synonymous words. They're synonyms. So tile also means voxel, and value also means type. And I just do that just for some clarification, and a shorthand way to get some good clarification. So pixel 3D, pixel index 3D location, right? So that's good there. Now, do I really want to call it sample projection geometry? I don't know if I do want to call it that, but we should probably just leave it as a comment above here in case we... So, I don't know. I think it's a good name. I just think it's a little bit verbose. So I think I would rather call it, take these two variables, and we need to convert it to whether it is on or off. So technically that's a bool. Actually, it's a bit, right? Because we just want to take this, sample the projection geometry, and convert it to... so it's a tile val and pix d3d, convert to bit, right? And that's kind of like a really weird function name. But the idea is that I want my function names to, rather than trying to come up with like new names and invent these new concepts that I have to juggle around in my head, I'd rather have a function name that exactly describes what is happening. So tile value, and right, so the exact variable names, C2 for convert to, and we're going to convert it to a bit, right? And the bit is either going to be 0 for off and 1 for on, right? So does a pixel exist in this spot? Now, the thing is that maybe we'll have another transformation that that doesn't use a projection, right? And it does the same thing, right? It takes the tile value and the pixel's location, and it converts it to a bit, but it's not sampling projection geometry. So then we would need a more descriptive name. But you know what? For now, I think until we get that other function, which we'll probably never make, right? Let's not try to like be more specific than this just because we think we might need it. Now we can make a comment on this function that we're sampling projection geometry. So let's scroll up here and see kind of like what section of the code are we in. And I think we're in maybe the second degree functions. Yeah, we're in the second degree function. So now we need to make a third degree section. So I'm organizing all of my code in a style where I think you have to do it this way anyways in GLSL, but in my C code, I always write my C code without forward declarations. So that way, when I read a function and I see that the function calls another function, I know without a doubt the function it is calling is somewhere. Oh, and I see someone said hello. So let me see if I can move that up. Here, I'll move that up so I can see the chat. So I've been doing this by myself for like a few, what do you call it? I've been doing this by myself for like how many days now? I guess it's been around 16 days. So I'm not used to anybody chatting with me, but hello there. I don't know if you're still there, but I see you have said hello. I don't know when you did. Maybe I should have some type of volume control for that. So let's see how well I can multitask, because boy, I'm not too good at chatting and multitasking. So let's go back to where we kind of declared the usage of this function, and I want to take this exact comment and I'm going to put it above here just for a little comment that will remind me what this does. And it's going to return a unsigned 32-bit value, because we're going to use that as a bit. U32 used as bit. You know what? Let's not make a comment there. Let's just... So we're going to go from general to specific, right? So we're going to have U32 tile value, and then a unsigned 32-bit integer for the pixel location using a index that is three-dimensional, so D3D. I guess I could have named it I3D for index 3D. But you know, I've named it D3D, and now we're kind of stuck with that name, right? We want to reduce our mental search space, so once we pick a variable name that stands for a certain concept, we want to stick with it. So if we did something like this somewhere in our code, if we use this somewhere in our code and this somewhere in our code, and they both meant the same exact thing, it would make it a lot harder to search through the code base, because you would look for all instances of this, and you would miss instances of this, and vice versa. Awesome. I kind of figured that no one finds streams via Twitch. Yeah, I kind of figured that no one finds streams on Twitch just because, like, I hear they don't really have, like, a good algorithm. It's not, Twitch is not like YouTube, where they have some type of algorithm for finding stuff. So yeah, I kind of figured that if anyone found me, they probably would have found me from somewhere else, yeah. Okay, so tile value and the pixel location. So we might want to make another comment. Pixel XYZ location as 1D index, right? And that's just a reminder for what that means. It's kind of... So I am kind of using, like, a... So ever since, like, maybe 3 years ago, I started to do... I went kind of crazy with trying to write, like, really terse code. That's why my name is Kanji Coder. Kanji as in the Japanese characters that were stolen from the Chinese, or borrowed from the Chinese, however you want to call it. But when you... they're very concise, right? Like, you can use, like, if we want, like, a variable for water, right? We could just use, like, the kanji water, right? And then it takes up much less space than the variable water, right? And I was trying to create, like, very terse code by giving, like, class names exact kanji that represent them, right? And that was an interesting experiment, but I found that that the code just was not maintainable. Even with me being, like, really crazy and putting a lot of effort into trying to make it maintainable, I would come back to code that was, like, 3 months old, and I would be like, I have no clue what this does. But that got me into the habit of maintaining a very strict column limit. So if you... let's just put some breakpoints here, make sure I don't lose my spot here. But if you look at the code here, I'm pretty sure it's probably pretty obvious, but all of this code has a very strict column limit, and the column limit right now is a little bit under 64 columns. My hard limit is 64 columns. It used to be 50, but then I hated how things never lined up with my tab spacing of 4 characters, so I'm like, okay, we gotta make it divisible by 4. Let's pump up the 50 to 64, and that's kind of like how I got to where I am. It's also that I think that code is very linear, and because code is very linear, we should probably be using a vertical layout. So my monitor is vertical because I think code is linear, and it makes more sense to kind of scroll through it this way than to try to, like, scroll off screen to the right and left all the time. Okay, anyways, rant aside, let's try to stub this in and see what we can do here. So we're going to have to indent a little bit more, and we're going to make another section. So this is, we'll just call it sample projection geometry. So this is a kind of like a section header that describes kind of like what the function inside here does. And, you know, and it's named based on what the parameters are, right? So these are the 2 parameters, and we're going to convert to a bit value. Okay, So in here, we need to kind of figure out how that's going to work. But for now, we can just return U32.1, right? And we can write like a to-do. We can write like a very obnoxious to-do. Finish this, right? So we can go off our column limit and be obnoxious, and that'll make me absolutely want to fix it because it's going over the column limit. Now, this needs to be fixed. We added some extra indentation, and now we've gone over our limit. So we could just say loc for location, or maybe location is redundant. You know, I think pixel XYZ as 1D index probably makes enough sense, right? And that also helps me. So I'm a very verbose person, but by sticking to a very small column limit, it helps me go, okay, I'm over my column limit. How do I write this comment a little bit more terse? And this is tile / voxel value, right? Okay. So let's make sure this works, because I'm sure that I'm pretty confident that I have made some type of screw up, because I pretty consistently make syntax errors. So let's test it out, and indeed I did make a mistake somewhere. So let's this is getting out of control, where there's so much code in here that when I try to scroll through here and find it, it actually consumes a little bit too much time. Some condition I don't know yet. Okay, that actually makes a lot of sense. So let's go look for some condition I don't know yet. All right, so we don't know exactly how this function is going to work yet. So I just kind of stubbed this in, right? Because I know that something has to happen when we're marching into the voxel. I don't know exactly how this logic is going to work. It's probably going to work exactly how the marching into the voxel map works. It's just going to be where we treat the voxel itself and the pixels within it as like a sub-tile map. So let's just call this a U32, and we'll just set it equal to 0 right now. U32 0. Now it could be bad that I'm kind of throwing around unsigned integer 32 all the time, because I think that a lot of GPUs do not work very well with unsigned values. But the thing is we're going to worry about being able to comprehend the code first, and optimizations are going to come very last. So optimizations may never come, because it's just one of those things that, you know, once we've perfected what we're working on, then we can optimize. But for now, we just want to get things working. And to get things working, we just want them in whatever way works the best for us. So let's take that and let's just make sure that works, right? Because we've... I think that somewhere we have made a mistake here. So it's saying no overloaded function. And, oh yeah, because these variables don't exist. We've just been kind of... so we need to take the... do we really want the XYZ and this ray world normal? Oh, we have the whole voxel object in here, don't we? So that might be a little bit wasteful, but I kind of understood why we took this first voxel object, just because we don't know what we would have needed, and so I just kind of like threw it all in there. So I do know that the tile value is going to be... it's going to be U32 tile value equals the voxel object dot the voxel... God, what was VOC for? Forgot what VOC stands for, but I know that the value is in there. I think it might be voxel coordinate and other stuff. Let's look at the struct for vox000. So let's take this and uppercase it and then search for the exact case and see what the definition is, like up at the top of the file. Oh, voc means voxel current information. Okay, got it. So, yes, when you're a little bit terse, there can be some disadvantages. But fortunately, from reading a lot of shader code, it looks like shader code is very friendly to writing code tersely. Like, my code is probably very verbose for what people who write shaders usually do from seeing the shader code on ShaderToy. So I feel like my style of terseness is kind of conducive to shader code. Okay, so now that we know that, we've kind of had a little review there, we can sample projection geometry. Let's go back to where we're kind of like setting up that call. So we're going to get the voxel value. So now this could be a problem where we have this as tile value, but then the member is value. But the thing is that there could be a lot of other things that are called value. So I feel like it's going to be easier to just call it tile value. Now, the other thing we could do is maybe instead of calling it tile value, we could call it vocval for a voxel value. And, you know, that is legitimate, but I think that I want to keep to the idea that our voxels are just a 2D tile map that has an extra axis on it. So I think I want to keep to tile map analogies rather than voxel analogies, right? So with that said, let me go into my kind of like my master shortcuts here and just see, like, do we have a thing called tile value? I believe we do. Oh, I guess we don't. What about this? Do we have that? No. Oh, I guess not. So we're gonna like make a note of this in our shortcuts. And so basically I just create shortcuts for all of the variable names I create. Well, not all of them, but sure heck a lot of them. And I do that just so that, you know, let's say it's 3 years from now, and I'm looking over this code, and there's no explanation in the code for what that variable is. There's a good chance that it's in this master shortcut list, and I can find it. So we have a variety here. So if I type the variable exactly as it should be, it'll put brackets around the variable and then put a little check mark to say, yep, you typed it correctly. So this is just, instead of IntelliSense, what I do is I just flashcard myself. So rather than being spoon-fed the answer and having kind of my brain degrade from kind of like being fed the answer with IntelliSense, I'll take a guess at what that variable name is, and if I'm right, I'll get a little check mark, and I'll be like, all right, cool. And then if I need some extra confirmation about what that variable name is, I usually use the word means for the definition, right? I could say tile val definition, tile val explanation, tile val whatever, but we want to reduce the mental search space, so I just stuck with the convention of saying means, which, you know, could be confusing if you think of mean as a mathematical average, but in this context, I use it for give me an explanation of what this variable means. So the explanation is this is tile value, right? Unsigned integer value in tile map data. Okay. And what else? So the other thing is I like to say that if it's backwards, so val tile, we're going to say that that is, we're not going to allow it to be backwards. So we'll say backwards, use, and then tile value, right? Okay. And then the other thing I want to do right now is voxval, and voxval. Don't do that. Okay. So if I try to use the variable voxval, hopefully I'll see this in my notes and know that I wanted to keep a 3D tile map analogy, and we should use this variable called tile value. Okay, so also let's make sure that the backwards is also in here. So val vox and backwards and wrong. Use keep. Okay. So now that we have that, what's next? I'm not sure what's next here. I'm a little bit tired. This is my what do I do? So once a week, I allow myself to have a cup of coffee so that the coffee still works, because I drank a lot of coffee like every day for 5 years, and eventually it doesn't do anything. Eventually you just need the coffee to be normal. So this is basically Mondays is basically the day where I get high on coffee, like literally high on coffee. Which is cool, because I think that there's some things that I don't think modern technology would exist without drugs. That's just my opinion. Also, you have to think that think about analogy of a magnifying glass on a piece of paper. In 1 second, you can take well, maybe not 1 second, it probably takes like 6 seconds, but in just a few seconds, you can take a magnifying glass in the sunlight and burn a hole in a piece of paper. But if you kept a piece of paper out in the desert for like 5 years, that piece of paper would never combust. Even though it's absorbed a lot more energy over that period of time, you never burned a hole into that piece of paper. So sometimes the concentration of energy actually achieves something different than having how do I say this? Sometimes it's better to be manic depressive, where you have highly productive phases and then highly unproductive phases, because you're like a magnifying glass. When you're switched on, you're burning holes through that paper, you're getting stuff done. You know, it's like yeah, I don't know if that analogy makes sense. Let's just continue. So tile value, and we need the three-dimensional index value, and I believe that is already a value within the voxel data. So we can go to d3d and we can say vox and 000 dot voc dot pix and d3d, and we can take a look really quick and make sure that that is actually a thing that exists. And it sure looks like it does. Yep, it's and it is a oh, I can see why it's a integer. So this is an integer because we don't have to worry about these location values. We don't have to worry about making them unsigned, because their location within the texture data, when we eventually put this into a texture, these locations are represented by where the data physically exists within memory. And so these values can be signed integers because of the way that they are derived, right? These values are not encoded in some type of integer on the texture. They're actually encoded in how we read the texture and look at the sequence of pixels within the texture. So we can keep these as signed integers, and I know why we did. We kept them as signed integers because sometimes we can go out of bounds, negative, or we can go into negative or positive out of bounds, and we don't want some weird integer underflow because we used an unsigned integer from doing that. So that's why I made those signed. But yeah, we can see that we do have the pixel index, one-dimensional here, which represents x, y, and z as a single number. So we do have that. And let's see. So we have that, and I think that's all we need for this to be proper. So let's clear those token highlighting and go over here. Okay, so that's kind of stubbed in. Let's make sure that this works, because I may have missed something when I stubbed this in. And I have missed something. Let's see what I missed. Oh. Boolean expression expected. Okay, so this I get. So GLSL isn't exactly C code. It's pretty much like C code, but not exactly. So it looks like this needs to be greater than or equal to U32 1. So I'm just saying, you know, if it's 1 or greater, it's true. So let's take that, and cannot convert from high P int to high P uint. Oh yeah, so the tile value is unsigned, but the index is signed, and so now that we know that we have the unsigned and signed, we have to change the signature here as well. So this is a signed integer. Also, these are type defs, by the way, or not type defs, they are defines. So I just like to keep my code as uniform as possible. So up at the very top of the file, we have all the basic types we've been working with, and basically these don't line up very nicely because they're different amounts of letters, so I just wanted something where everything is nice and uniform. So if you're wondering about that, that's why it's like that. Okay, so we've changed the signature. Let's take that, and let's see if we can get that working and see if we missed anything or not. Okay, so that is running. Let's take a look. Okay, so no change. I don't expect any change. We're still trying to stub in the data. So, boy, oh boy, oh boy. Sample projection geometry. Let's think about the logic here. So, there's a lot of different places we can start attacking this problem. And rather than be overwhelmed about, oh god, where should we start, just start from wherever you have an idea of how to do it, right? So in a lot of, like, what do you call it? Test-driven development and maybe lesser extent clean code, they kind of say, like, oh, write the tests first and then write the code. I don't agree with that. I think that you should, sometimes you want to start from the API side and work towards the inner guts, and sometimes you want to work from the inner guts outwards to the API, and you just want to start at any point where you actually have a clue about how it should be written. And it can be, because sometimes you have a much clearer idea of one of those or the other, right? And if you're going to give this hard and fast rule of always start with the API, when 50% of the time you have a very clear idea of what the guts look like, but not what the API looks like, you're basically kind of like shooting yourself in the foot like 50% of the time, because you're adhering to this dogmatic rule of like, just, oh, always write the API first, and then like write tests first, and then write the guts. Like, yeah, I don't believe that. I mean, like, it's good to have, like, I will say that structure is good. Even if your structure isn't idealistic and it's not perfect, even if your structure is not perfect, it is good to have structure. So if you have a corporation and they have like a structure of clean code and test-driven development, that is much better than not having any structure at all. So, right. Oh, anyway, so let me stop ranting. Let's try to figure this out. So the first thing we need to do is we need to take this and extract the the three-dimensional coordinates and extract XYZ from D3D. And so I know this is not a shortcut yet, so I'm going to think about different ways to type this out and create a shortcut for this so I will make less mistakes, right? Because I know this is an operation I'm going to need a lot. XYZ to D3D, XYZ to index 3D, and XYZ oh yeah, that actually doesn't make sense. So let's sort this here. So I'm just kind of writing shortcut paths in the source code. I'm going to put it in a different file once I have it. Try XYZ to, so really what we want is D3D to XYZ, or C to XYZ, yeah. Let's have a pick. Okay, so there's two ways we can convert. We can convert a three-dimensional index to x, y, and z, or we can convert an x, y, z to a three-dimensional index. So we have this x, y, z, and then we have a phrase. And so let's take all of this, and let's change. Let's kind of flip it around, right? So let's paste the phrase so that so D3D from XYZ and index 3D to XYZ, and then D3D to XYZ, D3D to XYZ. Okay, and we can keep this long-handed extract, right? So we can say extract D3D from XYZ, and maybe get D3D from XYZ and get XYZ from D3D, right? So different ways to type it. What about D3D? Does that have anything yet? No. So D3D, we'll say try D3D options, paste line, and then if we do XYZ, does XYZ have anything? Nope, XYZ, so we'll say try XYZ options. Right, so this is like, this is good, having a whole bunch of synonyms for how we can get to these two commands in our shortcuts. But if it's like a year from now, we might have absolutely no fucking clue, right? And so we might just want to have these little tiny tokens that will kind of put us on the right path to finding kind of this stuff. So XYZ options and XYZ options, XYZ options. And we'll say pick XYZ CTO, right? So, and then we'll put like a little or and a dot 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 for, hey, maybe we'll fill this out with some more stuff later, right? And then we'll do the same thing with the D3D options. We'll say D3D options and D3D options. And we'll say to pick D3D CTO for convert to and dot dot dot, right? Okay, so if we pick one of these things, if we pick XYZ CTO, XYZ CTO, XYZ CTO, if we pick one of these, then XYZ CTO CTO dot 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 uh, x, we'll say that XYZ CTO D3D, and then or why not just put D3D CTO XYZ, right? We might as well put them both there. We don't really have much anyway, so XYZ convert to whatever is going to be this, or the inverse of it is listed there as well. And then we can do the same thing for the D3D CTO, right? So D3D, and we'll take that, we'll paste it here and here. And then we'll say D3D over here, D3 and D. And D3D, D3D, yep. Okay, wait, nope, we don't need to do that, right? It's the same exact commands, but just a different header. So D3D CTO S in bubble brackets. You know there's another word for them. Oh, parentheses. And this is just like a prompt to say that here are the related commands that kind of start with, that are related to this, right? And that's kind of good for that. So for this kind of list here, we can do remove dupes to remove duplicates. And so now we have a unique list of prompts that will give us these values. And so now we can take all of these and we can do barg, and that's going to take them and give them bar arguments and put them all on the same line. And now we kind of have stuff ready to put in our shortcut list, right? Also, we have one problem. We did not actually create shortcuts for this data here, right? We created everything to route to there. So D3D CTO XYZ, D3D CTO XYZ, and D3D CTO XYZ, and to do snippet, right? So we're going to put a snippet here that we can reuse in future code. And we're going to look through our source code for that and just put it into a file that we can reference later. So for this, same thing. We got to take these, go XYZ CTO D3D and XYZ CTO D3D. Okay. So that looks pretty good. We're going to take all that, and we're just going to, let's just put some crap right here so that it'll fail to compile here, just as a quick note to, hey, that's where we need to come back to later. And let's put these new entries into our shortcut file. And you'll notice that in my shortcuts, I always put the new shortcuts towards the top of the file. And there's two reasons for that. One reason is the sorting algorithm for sorting the shortcuts. It will crash the first time it finds two shortcut synonyms that are identical, because when you type a shortcut phrase, that phrase must be unique. So the I have a tree sort. Well, it's kind of like a tree sort mixed with a hash sort that kind of sorts all of this data. And the first time it finds two keys that are identical, the whole thing crashes on us. And it takes a really long time to sort. You know, I've optimized it, but the thing is it's written in AutoHotkey, and AutoHotkey is kind of slow, and this file is 300,000 lines, because I've been adding to it for over 3 years. So if I put these new shortcuts at the end of the file, if I've made a mistake and I've added a collision somewhere, it's going to take like 5 minutes, and then at the very end of loading, it's going to crash on me. And that's going to consume a lot of time, so we want the crash to happen as soon as possible. So we put the new data at the front, so that the new data, if it's going to cause a crash, will most likely cause the crash sooner than later. Also, it creates a very linear list of everything I've been doing, right? So if I want to know what I've been doing for the past 3 years, I can just keep on scrolling down here forever, and I can see all the things that I've watched on YouTube, and all the things that I've been looking up on YouTube, all the PDFs I've been referencing, all of the math books I've been taking peeks at, all of the little code libraries I've been reading, all of the little formulas I've been working on, all of the different variable names I've been using, all of the little notes and text files I've been using, all of my ideas, anything that I've been up to. Sometimes I watch YouTube videos and I transcribe them as I watch them, so I have like very exact timestamps for certain things that were said. For example, we're in the middle of a pandemic, right? And so a lot of people are talking about like the aerolization of viruses and how they spread. And so when we want to talk about like water droplets and the virus spreading through the air, you know, for aerolization of COVID, there's this link on YouTube right here, and it goes to the exact timestamp of a Korean doctor talking about how aerolization of COVID works. So anyways, so there's a lot of stuff in here. And yeah, it is a little bit overkill, but the idea is I do not have a photographic memory, and therefore this is the next best thing to photographic memory. I've had a lot of code where it's just lost because I don't know where it was put, right? You wrote the code like 10 years ago, and you have no clue where it is anymore, right? So by meticulously putting a lot of upfront work here, where, you know, we're taking a lot of extra time to meticulously document, but the hope is that we reap some benefits by being able to recall things a lot faster. So I'm kind of ranting, but I am a little bit tired, so let's try to create these shortcuts now. So we already have the logic for that somewhere. So I know that it's like D3D in all capitals in my code, and so let's look for where that is. So so this is going to be the XYZ converted to the index. So we can take this and we can use that for one of our shortcuts, and then we need the inverse operation. So now let's make it easy to know where this kind of came from. So this is where we take the XYZ and convert it to the index 3D. So let's say XYZ, let's make an all capital version of this. And all capitals is for like a permanent shortcut. So it's like a permalink, but it's a perma shortcut. So it's in my shortcuts as this forever till the end of time, right? And these synonyms, like, there's the potential that those synonyms could change. In practice, they never change, but, you know, just in case. So now we have this kind of permanent shortcut, and now we can take this snippet, and we can say shortcut, and then we'll put that right there like that. And then we can maybe give it like a little outline or like a little section area, right? So we can take it and right. So now we have it kind of sectioned off where we know this is the shortcut and it's labeled shortcut. Sometimes I use SC for shortcut, but I think it's good to be more verbose than not, because I'll understand SC, but anyone else looking at that will have no fucking clue what that means. If somebody sees this, they'll probably understand what it means. Now, granted, you don't have access to my shortcut script, so that's not very useful to you. But you know, at least when you see the comment, you'll kind of know, like, what the heck it means. It's like a pre-made snippet that I had in my code, right? So, I already know that this version works. Now, we might want to make a little index of what these mean. So we're going to make like a little key here. And when we paste the shortcut, we can remove the key. But it's better to have the key there at our disposal in case we forget how it works. So key, delete this if it's already obvious to you. Okay, so the key is ntx, number of tiles on x-axis, right? And then NTY, NTZ, right? It's the same thing, but just XYZ, right? So very repetitive, right? But let's just be complete and fill all of that out, right? So XYZ, and we see X, Y, and Z isn't really used. The last, when we're doing the tile map calculations, usually the last component is not used. So if it's a two-dimensional tile map calculation, you only need the width, and if it's a three-dimensional tile map calculation, you need the width and height, but you don't need the depth. For bounds checking, you might want this, but otherwise you don't need it. So we can make some notes. So D2D is a index 2D, and D3D is index 3D. And are we missing anything? Yes, we are. Tile Y, tile Z, and etc. So, tile location, tile coordinate Y. So X, Y, Z. So same thing, take X, Y, and Z and just cut and paste. So obviously, if we cut and paste, if we activate this snippet and it cuts this huge block, right, we're not going to want to have this pasted into our code every time we use the snippet, right? So we're probably going to have this for reference, just so we can, if it's been a while since we've used this shortcut, we'll reference the key, and then after we've referenced the key and probably replaced these values with whatever values we need to use in our code, then we'll kind of just delete this key from whatever we've pasted. So let's take this XYZ to D3D, and let's save it. And we'll go into my shortcut files. Technically, I guess it's technically GLSL shortcuts. I mean, it's really just math, and it could be anything, but it's specifically written for GLSL, so let's keep it in here. So let's name the folder exactly the snippet name. So XYZ C2 for convert to and dex3D. And then we can shorthand name it here. So I'm going to just call it XCD and underscore, right? Then we'll take that and we'll put it in our XYZ to index. And now we have the snippet for that, right? So when you type this and press comma twice, it'll activate this shortcut. So this is what activates the shortcut. So this is the phrase, this is the data, and this is the action to take with the data. So it's going to take this data, it's going to use it as a file path and paste the... Oh, we don't want to paste line, we want to paste file. We want to paste the file contents of whatever is in here. Paste line will paste verbatim whatever is on the line. So that's pretty good. Let's work on the next one. So let's we have to do the inverse operation of this. So let's take this key here, and actually let's just cut paste everything really quick, and then we'll kind of like use what we need to do. So let's take this and we're gonna call this D3D C2 XYZ. Okay, and we're gonna take, we have to somehow do the inverse of what is in here right now, right? So let's comment this out and think about how do we derive the inverse from here. So there's a lot of different ways to do it. Well, there's not a lot of different ways. There's actually two ways. One uses modulus and the other one does not. And the one we need is we need index to xy no modulus. And it looks like dex to xy no modulo. I know I made a shortcut for this a while ago, so modulo index to xy. Ah! So that was close, but it also has modulo, so that's not what we want. No mod index to xy. No mod. Do we have a shortcut for no mod? Okay, so itxy no modulus. Okay, cool. So we do have a... So remember how I said, you know, when it's been like a few weeks or a year, you might not remember any of these synonyms, even though you've written a lot of synonyms. There's still a lot of combinations and ways you could phrase something. So it's good to have like a shorthand version where you where after you've forgotten everything, you have like a little nibble that you can kind of find what you're looking for. So with that, since that's what kind of saved me here, we're going to say no modulo and see if that also gives us stuff. No modulo? No. No modulo. No modulos. I can't spell modulus, so no modulus. Okay. No without mod and no mod. Okay, so we're going to take this and we're going to say try itxy no modulus. And we'll date this one. So we'll say this is on 2020-1201. Okay. And we'll also take this and we'll go barg and we'll say try itxy no modulus. And also we need a new shortcut, so so this is the other one we're going to need eventually. So let's do 2020-1201, and this will be A, and we'll paste this, and then we'll take the same exact shortcut, and we'll call this B. So this is just a little tag to let me know when the shortcut was created. So I have an idea of like, how old is this? How relevant is it? In case I ever come across very similar shortcuts that are kind of the same, I kind of know which one is the more up-to-date one if that ever happens. So, and also since these are almost identical, we have the A and B, so I can find it within the source code really easy, right? Because we have this A for one of them, and we got the B for the other one. Okay, so with that, we need to make this still. We still got to make this, but we have a hint that we can find the two-dimensional version of the math, and from the two-dimensional version of the math, we'll have a better foundation for how to derive the three-dimensional math, right? So rather than guessing and trying to think about it again when we've already solved the problem again, we might as well look at how we've solved the problem previously, because the previous way we've solved the problem will likely formula expects integer inputs to work. Okay. So we take the index and we divide by the width. Okay, so this is going to be truncated, isn't it? So this is not the best way to do this. So I feel like we have a better way to do this. So let's see if I have like a itxy no modulus 2020, right? No, we don't. itxy no modulus. We're gonna make one though. Okay, and the reason we're gonna make one is this does not look quite correct for there's a lot of casting that needs to be done from what we've done earlier. So if we go into our code here, somewhere we're going to have, so actually if we look up, let's go look into, we're going to open AAC 2020. No? Open AAC 2020. Use open AAC 2020 folder. Yeah, okay. So, I'm going to call this open AAC, and I think I can do it with dashes. Open AAC 2020 folder. Can I do it like that? Nope, I can't do it like that yet, but we'll fix that. So, okay, so I have some code I've written before that I think is written properly, and it's shader code that will work properly. So let's look for open AAC 2020 folder. And let's paste the snake case version of that so that I can find it later again. That's just so that I can make sure that I have an exact match, right? By making the all underscore version, I can easily double click it and kind of search for it. So that's why I do the snake case in addition to kebab case sometimes. Okay. So within this project here, which I've been working on, this is like a C project, and within my dependencies, actually not my dependencies, my library, I have default shaders, and inside these shaders they have like a simple tile map math, and I believe we had to convert the x. Oh, we only do XY to index here, do we? So let's see. Yeah, this is index to XY, which we already have done, right? We've already done index to XY, and we're trying to do... Oh, wait, no. Hold up, hold up. Let's go look at this for a second. Did we... XYZ to index, XYZ to index. Okay, yeah. So this is that, and then we just got to do the inverse. So we're trying to do index to XYZ. And in here, we have tile X and tile Y, and we're deriving those here. So this is the correct math that we need. So let's just steal all of this code here. And... Oh, wait. Oh, this is just the inverse. Okay, yeah. So this is what we need. So let's take this, and let's just paste it down here. And right now I know this code works, so we could just take this and call this ITXY no modulus 2020, right? It's index to XY, and let's look at this. Width and height, right? So width and height, and you know, I'm not going to worry that it's not quite... I'm not going to worry that maybe the variable names are kind of like hard. It's kind of hard to remember like what it stands for, but it's good enough for me where, you know, you just got to take a little bit of look at it and you'll kind of get it. So I'm going to take that and we're just going to make this into a shortcut. And as far as what these variable names mean, we can say that, you know, we can maybe have a note as to where to check for the variable names. So we can say maybe like for working reference, C. Okay, and then I can just have a little reference for where I can find that, right? And we'll take this and we will put this somewhere as well. Okay. And we'll save it in a folder with that exact name. Let's open up... Okay, yeah, now let's save this. Okay, so let's back out one, and we'll save it at... We'll make a folder name, new folder. Okay. And all capitals, just because that's the way I like to keep things. And then, I'll just call it ITXY, and copy that path to the clipboard, and then we'll say, we'll just do edit file just because it's kind of big. Okay, and then we will put this in our shortcuts as well. So we'll go over here, and we'll paste that. And the reason for that is because we have this here, but when we looked at it, we really want an implementation that has the correct casts. This isn't as nice as I would like it. It's still kind of like a dirty shortcut where it's not as perfect as it could be, but it's good enough to where if we start coming back to this type of shortcut over and over and over again, we can refine it and make it better. But for now, I think that works fine. So with that, let's now that we've changed that, let's look at this again. So where are you? Okay. Let's take this for reference. And let's go into this file, and let's, well, we could keep that open, but this is the one we want to edit. And we want to figure out how we're going to get, it into a XYZ. So we know that we're going to start with D3D, and we're going to whittle it down. So we know the first things we're going to get are going to be TX and TY, I think. Or actually, no, it's, yeah, the last thing will be X, so, so I think this is TY, and this is going to be TZ. And this is our index, and it's going to be our index 3D. And index 3D is an integer, so, so why is there no truncation here? That doesn't quite make sense. So we're going to do float32. We're going to use our float32 type defs in here. And actually, we don't need to, yeah, float32, and we'll divide these. So the width, nt number of tiles x, and this is probably ntz maybe. I'm not quite sure what they need to be yet. I'm still kind of thinking about it. So this is probably completely wrong. So let's think about it. We got to, the first thing we can do is kind of figure out how many, to figure out the z value, we need to figure out how many full cross sections we have, right? Yeah, how many full cross sections we have. So we gotta take all of the pixels and figure out how many full cross sections go into that. So to get the full cross sections, we need to take ntz. We need to take ntx times nty, right? So ntx times nty gives us one cross section, and for every full cross section, we get 1 tz. Okay. So if tz is equal to 0, then that means ntx times nty will be, that'll mean that if tz is 0, that means d3d is less than ntx times nty, because we don't have enough pixels worth of, we don't have enough pixels stacked together to fill a complete cross-section. So this is what we need first. Convert everything to float 32. And then we need to use trunc to truncate this, right? Because we just want, we don't want the fractional part, we just want however many full cross-sections there are, right? And the next thing we want to do is we want to convert that to an integer. So we'll do an integer cast last. Awesome. So I'm pretty confident that this is what we need. And so now that we have the now that we have derived z, we can kind of figure out y, right? So or actually, no. Now that we've derived z, we can after we've derived z, so it's kind of wonky the way we're going to derive this. So but no, actually, after we derive z, we have to derive d2d, right? So so int d2d equals this is our given input, given known input value, right? So we can make a note that that d2d is our given input value. This is the thing we know. It's our known. So we'll just make a note of that in our snippet, so that we know we can just delete that line if it is already provided, or we can fill it out with whatever we need, or we can use a define, whatever we need to do. So also, that's not correct. It's d3d. d3d is our given, and then d2d. So what is d2d? d2d is the d3d minus however many pixels are used up by the filled cross-sections of the z value. So tz multiplied by, and we don't need parentheses for this, but I feel like it's going to be easier to reason about if we put parentheses around it, right? Because then we can read it correctly, okay? Because it's the tile z multiplied by the area of the cross-section, right? And then minus, okay. So now that we have the two-dimensional index, we can now just use the standard, the standard tile x, tile y kind of math. We can just use that again. So we can take the, so this was wrong here, so we can just forget about that. And so we can say that this tile x, and we can just fill this out now. So tile x equals well, that's kind of weird. Hold on. So let's do index to xy. So we already have a pretty good snippet for this already, so let's just use that snippet. And let's just rename some things. So tx and ty. Okay, and then this index is going to be our dex2d. Because we've already, right here, we took the three-dimensional index and we carved off all of the pixels that were used on the z cross sections, right? So we took all that away, and once we shave off the z cross sections, we're left with only one layer, which is a tile map that has not been all the way filled up with pixels. So now we have a two-dimensional index, and this kind of sucks here because this is not this one uses modulus, so that's not going to help us. So we're just going to have to reason about it on our own rather than rely on our shortcuts. So we need to kind of do the same thing we did here. So int ty equals the int trunc f32 d2d, and divided by f32 and number of tiles on the x, ntx. Okay. So what we're doing here is we're taking all of the pixels on this cross section, all of the pixels on the x and y of our cross section, and we're going to divide by how many filled, oh, that's wrong. That should be NTY. We're going to divide by how many filled rows we have, right? So if NTY is 0, that means we have 0 filled rows, and, well, hold on. Divide by zeros are bad. Is this right? Oh, sorry. No. This is not like the current tile value. This is the number of tiles on the Y, right? So we're taking, this is a quantity of stacked together pixels. And we're just taking this quantity of pixels, and we're trying to figure out how many rows we can group it into. How many rows can we create from all of these indices, right? So this quantity of indices, how many rows can we group that into, right? Oh, okay, yeah, so I see where we're going here. So that's why we're doing it by ntx. So number of tiles x. So yeah, okay, that makes sense. So because this value changes, this value doesn't, and the number of tiles on the x for every filled row. So for every filled row we have, we get another ty. So we take all of these pixels and we figure out how many filled rows we're gonna get, right? And then we gotta truncate the result and convert it to int, but then we'll get our ty value. Okay, yeah, that makes sense. And after we do that, we have the last part. So tx is going to equal the dex 2d, right? So we take everything we had, and we're going to minus the ty times, rather than the cross section, we're just going to subtract the strip this time, right? So the number of tiles on ty times ntx, right? So another way to think of this is, hold on, ntx. So another way to think of this is the width, right? So the y value, how far down on the y, multiplied by the width. So how many pixels per strip are going to be filled for every time you go down one on the y, right? And so this is the total number of pixels for the number of filled y's, right? And then we'll take d2d and we'll minus all the pixels taken up by the filled y rows, and whatever that remainder is the tx. Okay, so that looks pretty good. That took a while to derive, but I think that is correct. So let's make sure that all the variables are accounted for here. And actually, let's do 4 and 5. Okay. So we have cyan, we have orange, we have yellow, and we have purple and green. Let's do just these. So cyan, orange, and yellow. Cyan, orange, and yellow are used, and then I'm going to guess that the NTZ or one of these is not used. So let's highlight all of these and see. Okay, NTZ is not used. That actually makes sense for why NTZ is not used, but X and Y are. Let's do some cleanup. So let's get rid of that. And do that. And maybe, can we get a little bit of indentation there? Because that would be nice. Really close, but not quite. What we could do is we could do define T as trunk. And truncation is going to work on float 32 values, so we'll have to make sure that that they're float 32. So undef T. Okay. So that looks pretty good. So with the trunk here, we can replace that with a T like that, and now see how we have a little bit more space. This still looks kind of chaotic, where maybe we could line some things up a little bit better. So it looks like there's D3D, and then I want to see where they're kind of related here. So D3D minus, and then there's like this, let's get rid of the coloring for a second. So F32, are our brackets balanced correctly? Yep, our brackets are balanced. Can we... Okay, I just like that lined up very nicely, and then, sure. And this last one is going to be similar to this, right? Yep. So let's, we just want to, like, put everything to where we can kind of see the obvious patterns. We can make the patterns in the formula more obvious if we kind of line everything up. And then it'll hopefully make some mistakes more obvious as well, is what we're also hoping for. So, so NTX, right? So we see an obvious pattern here where NTX is everywhere. NTY is at the beginning. We have float 32 cast, so we see how we're kind of like going from a XY, we're going from index to X to an XY value to index to XY value to XY. So there's a little bit of like crossing back and forth. And we'll do 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so anything with 2 consecutive underscores or more is reserved for future GLSL variable or function names. So this will not be allowed, so that's a nice placeholder, right? Because it's kind of bolded by these underscores, and it lets me know that I need to fill this out. So when I use this snippet, I'll know I need to change this or delete this if D3D is already defined. So let's look at the math and make sure that this math makes sense. So actually what I'm going to do is I'm going to actually draw this out while I'm looking at the formula and make sure that the formula kind of makes sense while I'm drawing it out and see if I've made any mistakes. And the reason for that is just I really don't want to take the time to like rewrite this in JavaScript or rewrite another shader to make sure this is right. But I would also like to make sure that this is correct before I add it as a snippet. So we need to do our due diligence and work through the math to make absolutely sure that this is correct. So let's go to our camera, and let's just make sure that we're right side up here. So let me just write hello. Okay, so we're right side up, and let's think about the math. So let's do a volume that is, let's say 4 by 3 by 5. Actually, no, let's not do that. Let's do 3, 4, 5, just because that's going to be 3 by 4 by 5, right? So we're going to have this volume that's 3 by 4 by 5. Okay, and we're going to do like a little orthographic view so I don't have to worry about my horrible drawing skills here. So, you know, we're going to have 3 over here, we're going to have 4 here, so this is the XY, and then Z is just a whole bunch of extra layers, right? So 1, 2, 3, 4, and 5, okay? So from here, let's just draw that out, and then this is 5 here. Okay, so with that, let's take a value that's somewhere in between. So let's get out a calculator, and let's multiply 3 by 4 by 5, and then let's divide by 2 and see what kind of value we have. So 3 times 4 times 5, right? And 3 times 4 times 5, what do we have? We got 60. Okay, so 60 divided by 2 is 30, and I kind of feel like that might be... Well, you know, let's just go with it. Let's just go with 30. So we're trying to take the three-dimensional index of 30 and figure out what the xy is, right? So d3d equals 30 yields... What does that yield? Okay, so let's look at the camera again. So now that I've kind of... okay, so camera... Okay, so if the d3d is equal to 30, what xyz does that yield? So let's actually work it out by hand, and then kind of figure out if we have it correct. So the first thing is that we see for this cross section 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 3 times 4 is 12. So we're going to take 30 divided by 12. And let's look at our screen here. Do we have something where we're dividing by x and y? Yeah, we have ntx times nty, and we're dividing the entire index by d3d. So it looks like so far that math looks correct. And so 30 divided by 12, I can't do math in my head. So 30 divided by 12, what's that going to give us? Okay, all right, it gives us 2.5, right? So 2.5, and the thing is we're going to truncate that, right? So that's going to yield 2, right? Okay, so 30 divided by 12 equals 2.5, but we're going to truncate it, and when we truncate it, we get a 2. Okay, so the 2, what is that in our formula? So we did this line, and that should be our z value. So our z value should be 2. So we think that tz equals 2. Okay? So that means over here, we're not on this cross-section, we're not on this cross-section, but we are on this cross-section here, because this is cross-section 0, this is cross-section 1, and this is cross-section 2. And instead of thinking of it as cross-sections, you could think of it as the z value. So let's highlight the cross-section area. So here is... or actually, let's not give it a color. Let's actually just kind of like give it like a little crosshatch here, right? So these are our cross sections, and we are on cross section 2 most likely, because we say tz equals 2. Okay, so After we found TZ, it looks like we want to get whatever's left over to get dex 2D. So D2D is going to equal the three-dimensional index minus whatever whole. We're going to calculate the modulus of that division and get whatever's left over. Actually, that's not quite what we're doing. D3D equals the TZ. The TZ times NTX times NTY, so that's 3 times 4. That's 3 times 4. And that's NTX, and this one is NTY. So TZ times NTX times NTY, and that's going to get us D2D. So let's look at actually the code over there. And what do we have for the code? Obviously, this is a horrible view. There's a lot of glare here. But dex2d, we can see that dex2d equals the three-dimensional index minus the tile z value multiplied by ntx times nty. So basically, tz times the cross-sectional area of a single layer on our three-dimensional tile map. That's what that is, okay? So now that we've looked at that, and that looks good to me, so TZ times 12, basically, right? TZ is 2 times 12, 2 times 12, 24, right? So dex 2D equals 24, right? So 24 is the index 2D, okay? And with index 2D being 24, hold on. Does that make sense? TZ is... Oh, hold on. Oh, we screwed up here. How the hell did I get... No, because TZ is 2. And we have 3 times 4, that's 12. 12 times 12, 24, right? So dex 2D is 24. So I think we have made a horrible mistake somewhere. Okay, so I think we've already screwed up this calculation. Because 24... 3 times 4 is 12. One of these cross sections is already oh, hold on. D2D, dex 2D, TZ times, that's not dex, we have to take D3D, which is 30. Okay, so we're not, no, that's just not correct. So right, D2D equals the D3D, D3D minus TZ times 3 times 4, right? And so this is NTX, NTX, and NTY. Okay, so that's NTX and NTY. TZ, and the part we forgot was the D3D minus, right? So the dex 3D is 30, it looks like, and how do we calculate dex 3D? Dex 3D is our given, so given, right? We started out with it, we want to know where it is, right? So with that, dex 3D, let's do D2D equals dex 3D, oh no, sorry, D2D equals 30. We're going to fill it out. So 30 minus, what's the TZ value? TZ is equal to 2. 2 times 3 times 4. Okay, so 3 times 4, 12, 24. 30 minus 24. So D2D equals 30 minus 24. Okay, 30 minus 24, 6 left over. So dex 2D is equal to 6. Okay, 6 actually makes sense, right? Because 3 times 4 for the two-dimensional cross-section means that the highest index is 3 times 4 minus 1. So 12 minus 1 is 11. So it's 0 to 11, right? So this is tile 0, and the last tile right here is 11, right? And the 11th index is the 12th tile. The 0th index over here is the first tile, okay? So 6, we can figure out where that is. We can actually, without even doing any math, we can figure out where that is, right? We can go 0, 1, 2, 3, 4, 5, and 6, right? So the coordinate is going to be 0 on the x and 2 on the y. So we know the answer is going to be, we already know that tx equals 0 and that ty is equal to 2. But now we can check that as we're going to still do the math and make sure that's correct. But now we can verify that from our diagram. So ty is equal to the dex 2d divided by ntx. Okay, so ty equals d2d, which is 6, divided by ntx, and ntx is 3. Is ntx 3? Yes, ntx is 3. And we're going to truncate that value. So we're going to truncate basically means we're going to floor it. So in this case, 6 divided by 3 is just a 2. So we got 2. Ty is equal to 2, and if we check our little ledger here, in fact, we've already verified it in our diagram. Ty is equal to 2, right? Because it's 0, 1, and then 2, because it's that 6 right there we're trying to get to, right? Okay, so Ty is equal to 2, and Tx equals, and it equals dex 2d, and d2d is 6. And we're going to subtract the ty, and ty is 2, we already calculated that, times the ntx value again, and ntx was 3, okay? So 2 times 3, so 6 minus 6 is a 0, right? So tx is 0, and tx in our little key is 0. So I'd say we have that math correct. So that was a pain in the ass, and I don't want to... And that's why I kind of create snippets for this, because, right, that's a lot of work, but the thing is that, this is very error-prone, right? This is, we gotta be very precise with this. I mean, maybe if you're like a genius, you know, I'm sure there's people who are smart enough to just write this the first time, do it perfectly, and not have any problems, but as far as I'm concerned, I can't do that, so I need to make absolutely sure this is correct, right? And, you know, there's still a potential that maybe I screwed up somewhere with my casting, but it looks like, let's check the bracket balancing. Bracket balancing looks good. Even though F32 is not like a... It is a define, but I use that define enough to where I know that F32 stands for float 32. So that's not a problem. So I would say that's good. I think this is good to go. So we're going to take this this name right here, and we're going to Control S. We're going to save that, and we're going to create a folder in our snippets, and we'll just put that right there. And now we have D3D converted to XYZ. So DCX, right? So the inverse of the other one. And we'll put that in our snippets. So where are we here? Right here. So DCX, right? This is XCD for XCD, and this is the inverse. So SC, there we go. So now we have the math is kind of like solved, and hopefully we've done it correctly for both these snippets, and we can reuse these snippets for the rest of our life and never have to recalculate that ever again, right? So the problem with why this took me a long time is usually I use the modulus operator when I'm doing this type of math. However, the GLSL modulus function is not integer friendly. It only works with floating point. So when we're using discrete units like pixels, it really doesn't make sense to be using floating point functions, like floating point modulus. So I'm not comfortable using floating point modulus with these types of calculations. Maybe I'm just superstitious, but I just haven't had luck, so I would rather just code it by hand without using modulus, right? So that's good. I think we got those shortcuts out of the way. Now the next thing is we can say that do we have like a DCX? So DCX, is that anything? No. Is DCX anything? Use D3D CTO XYZ. Or try D3D D CTO and XYZ equals X. Okay, maybe a little explanation of why I am saying that, you know, if you type DCX, this is kind of what we want. Then we can do the exact same thing for the opposite. So XYZ to D3D, and this is XCD and XCD, right? And XCD, and we just gotta swap these parameters around, right? So it's gonna be XYZ, then the convert to, and then the last one, right? So we're just flipping those parameters. So XCD, XC and D, DCD, wait, DCD, DC and X, DCX, Jesus, okay, DCX, XCD, okay, cool. So, with that, I think we have enough shortcuts for that to keep us happy. We might also want, because this is the first time working with these, it could be a good idea to have just a edit DCX, DCX edit. Okay. And then also for the XCD, also have like a command for editing that as well. So edit XCD edit, and then we'll have that there. So edit file. Okay. And this is a lot of housekeeping, but I think it's going to be worth it. So I'm kind of getting tired where it's like I can't quite think straight, so I think I'm going to need to stop pretty soon. Just because, yeah, it's I am getting tired. So let's try to wrap it up. So as we're wrapping this up, the most important part is that our code needs to compile, right? It needs to compile and ideally not have any like obvious bugs in it as well. So let's look at this. So obviously I know we did like we put some gibberish in here to make sure we would find the code that we needed to work with. And so I do remember that we're going to take the tile value and the pix D3D, and we're going to convert it to a bit, right? And I believe that's probably the exact name of the function, isn't it? Yep. So isn't that nice? Like, I'm really tired. My brain isn't working, but because I'm so consistent with how I name things, I was able to find this. Even though this looks weird as hell, I'm consistent as hell. So in here, we have this blah, 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 blah. Okay, so I believe this is where we need to convert the this pix D3D to XYZ, right? So, to XYZ, or pix D3D to XYZ. So I don't know if these actually exist, so if those shortcuts don't exist, we should probably make shortcuts for that as well. So let's check to see if we have these already. We may have already made them. And also that is flipped around, so this needs to be XYZ, XYZ. And let's do pix D3 D3D C2 XYZ, right? Write it like a conversion function, because I think I may have wrote that already. Nope, I haven't. Okay. And then we'll also do snake case, right? So snake case, and then we'll just, oh no, kebab case. Kebab case. And then we will take, this is the index to the xy, so this is the index to the x and y's. So we'll take this, and, you know, if we really want to, we might as well just, you know, I'm kind of tired of routing everything to that one thing, so we're going to say paste file, right? We'll say that's good enough. We know what you want. Take it, you know? Let's do the same thing with the inverse. So let's take the inverse function, and so we're going to take the XYZ and D3D. Once again, XYZ and D3D, D3D, and XYZ here. And this will be D3D, D3D, and this is XYZ, and this is D3D. Oh wait, hold on. D3D. Are these the same in the beginning and the front? Because if they are... Oh no, one is C2 and one is 2. Okay, so then DCX and XYZ to the index. Okay, and we'll paste that file as well. Okay, and maybe this was one we already put somewhere, right? Okay, nope, doesn't look like it. So with that, what we're gonna do is we're gonna so we have the 1D index, and let's just take the snippet, right? So this is the snippet we need. So right now we haven't reloaded our shortcuts, so we're just gonna cut and paste. And unfortunately, this takes up a lot more room and needs to be like indented like twice more than it is, right? So that kind of sucks. So how could we save a little bit of space here? So I guess the first thought is we can do I here. And then we can define I as int. And then we can undefine I over here. How else can we save some space? Also, we can define f as just, instead of f32, we could just do float. And then undef f. So anywhere see float 32, we can just do this, right? Okay, now we've kind of like, we gotta like line stuff up again. But we're getting somewhere where we're kind of like that's getting better. Now these are constants. TZ is not, I believe. Yeah, TZ can be a define over here, but we could also use it as a variable name. That's fine. So we could do D3 if we really wanted to. That would be, well, oh, hold on. We got a little space here. We can use I for int here, so that's nice. Bam! We got enough space. Awesome. So we've kind of changed this around, right? We've made it a little bit more terse, and now that we've kind of reworked that, we can we can take this and TINF, define and undef, TIFF, whatever, you know. TIFF is a file format, that's cool, yeah. Sure, why not? Why not? Let's keep it like that. Let's take that, and this is D3D to XYZ. So D33 to XYZ, XYZ to D3D. Okay, so this is the one. So let's take this and paste the new version right there, right? So it's going to take some reworking, right? Because there's a little bit of back and forth the first time we use it. But we wanted to make it take up less column space because this is where it's being used, and I absolutely don't want to go over this column space. So yes, I will add more space vertically to make sure I don't avoid here, because it's really easy just to vertically scroll like this. What is not easy is if you have to use this scroll bar and this scroll bar at the same time. That just makes the code really annoying. So let's not deal with that. So I'm pretty confident that this works. And now that we have the X, Y, and Z, we can think about how the cross sections are going to work, right? So first of all, we need to know if the cross section is additive or subtractive, right? So so first of all, if the tile value is greater than SDF, something like projection max something or other, if it's greater than that max value, then we're just going to say that a bit equals 1, right? So if we don't have any special projection geometry, then we're just always going to return 1. So over here, we're going to say return the bit. And, you know, maybe if you want to define bit as something more definite, so maybe you want to call it bit U32 or U32 bit. If we want to go general to specific, it would probably make more sense to call it U32 bit, so we'll call it U32 bit. And then over here, we'll say U32 bit, and we'll just say, really, I would like this to be equal to either 1 or 0, right? So as a trap value, we'll say 404. 404 not found, right? And that actually needs to be U32 404. So U32 404. And we can mark this as a trap value, right? And a trap value, in my terminology, a trap value is an intentionally incorrect value, so that if I see a 404 in this bit value, I know it's wrong, because this bit should only be 0 or 1. Bit should only be 0 or 1 when returned. Okay? Bit should be, and then since we're going over our limit, we can be a little bit more concise. Bit should be, we don't need only be, it should be 0 or 1 when returned, right? And this is a trap value. Okay, bit U32 equals 1, and we return it here. So otherwise, so else and else if tile value, actually no, if 1, well, that's not really it. So let's go and figure out what that is. So I know it's not SDF projection max. It is something similar, but not quite that. So also, I'm going to go to my Control F CTRL F index, CTRL-F index. I'm going to go to this index, and I'm going to say that I'm going to say a typo fix. I'm going to make a typo fix entry, and I don't know what it is yet, right? But I know there's a value that it's not quite this, and we got to figure out what that is, right? So it is up in the top in our configuration here. We have, oh, SDF projections max, right? So with that, we can scroll back down here to where we have like our index of different things. And we know that the fix is this SDF projection max, right? And while we're here, we can just kind of like line everything up and make it look kind of nice. Okay, so SDF. So I was pretty close. So PRG for projection, but I use PRG to mean project, and also I'm trying to keep my abbreviations as the first 3 letters of the word. So PRO for projection, right? Just because I think it's much easier if I'm very consistent with my abbreviation. So if I'm just shortening a word, I just want to take the first 3 letters of the word. Then I don't have to think about how to make the... I don't have to think about it, right? The less thinking I have to do with the variable names, the better. So I see kind of why I did it that way, and now I see the correct way. So now that we know that, we're going to look for the improper spelling to get back to where we were earlier. And if we're greater than this, then we have no cross-sectional data. No cross-sectional data to create interior voxel topology. So just return 1 filled for every pixel of the current voxel, right? So what we're doing here is we're just saying that if the tile value is greater than the max number of projections that we have, we're just going to say that we're just always going to return 1. So it's just going to be a filled voxel. So basically these voxels that we already have, it's just going to be a filled voxel like that, nothing special, right? So like this filled voxel here, this filled voxel there, etc. So, okay, so otherwise, else, if the tile value and, let's do SDF Pro 001 equals the tile value. And the reason why I want to use this Yoda expression, where I put tile value next, is so I don't accidentally assign tile value, right? I want to make absolutely sure that this is a comparison, and we can make sure that that is the correct variable. I'm pretty damn sure it is. Yes, we have the geometry, and oh, so this is the actual data, but the geometry is oh, okay, I see how it works. Okay, never mind. So if 1 equals tile value, and this is a U32, so U32 1, and we can just make a note that that is this is the geometry, right? So 1 is equal to this tile value, then this is the data we're going to use, right? And just put that in a little note right there, right? And then else, if U32 2 equals the tile value, then we're going to say SDF Pro 002 and do whatever else we need to do there. And then else then we have a problem, right? And as far as like how to handle that, well, we have this U32, right? And it's going to return 404 if it's not filled. And so let's add another trap value. So let's say that U32 bit equals 666. And actually, we got to do U32 666. And error code, right? Okay. And so we can try to handle the return from this, and in the return we can look for a 666 or just in general any value that's not 0 or 1, and we can use an error pixel value somewhere, or maybe we could make, since we're trying to fill the voxel pixel, we could have maybe an error of voxel, right? So we could have, sorry, not an error voxel, an error voxel pixel, right? And so, because right now we've been concentrating mostly on like error colors, but since we're at this higher level within the shader, it might be easier to have a error voxel pixel. So for instance, in the Hammer editor for Half-Life 2, when an asset is missing, rather than like crash the game, there's an actual error asset. So if the model is missing, in place of where the model should be is just the red text that is, it says error, and it just flashes red. I don't know if it spins around or not, but it definitely says error and it flashes red, right? So it lets you know that there's a problem there. So if the asset can't be found, it just replaces that asset with an error asset. And that's a nice pragmatic way to solve the problem. So this looks good to me. So with this, we need to figure out, well, what is the actual math for figuring out what cross-section, how that cross-sectional geometry kind of goes together. And we have to remember that the resolution of those cross-sectional values may not be the same as the resolution of those cross-sections may not match the resolution of our voxel tiles. So we have to account for that in the math as well. But I am getting tired, so I'm going to try to not do that right now and just say U32-bit equals U32 and we'll do 9001 to do actual logic. Okay, and we'll just like 2D, we'll make that kind of obnoxious because this is very serious. It absolutely needs addressing next time. And then we need to go over here, and we gotta go like 9002. 9002 because we have number 2 here, 9001 because we have the cross-sectional data number 1 right here. Okay, so with that, I think we're good to like to get out of here because I'm tired. It's been 3 hours. Holy crap, 486 drop frames. Anyway, so that looks good to me for now. We could take a few looks around, make sure that everything kind of looks like it's stubbed in correctly. So some condition I don't know yet. We can also make an obnoxious to do. What should this condition be? Right, so we can just make these kind of obnoxious little to-dos, right, that go off the column. So I like to go off the column when it's something that's temporary, right? So I have this very strict column limit, and when I go off the column limit, it's something that's temporary that needs addressing, so that, like, when we just scroll down here like this and scroll through here, we can just see the problems right away. Like, that sticks out like a sore thumb. We can see it right away, and we can address it, right? And so we have like 3 points that look like they need some addressing, which we'll kind of get to later. And let's go over here and see where that's called. So one problem, so we do have a problem here. Tile value and pixel index 3-dimensional to the bit. Well, I don't see any bit value, do I? Yeah, there's no bit value here. So we need to say somewhere we need to so let's just do it here. Let's say U32 bit is what we've been using. And that equals, right now that's kind of undefined, so we'll do 1, 2, 3, and we'll say that's a trap value, right? It's not a valid value. And U32-bit, and U32-bit is going to equal calling this function, right? And yeah, let's put another parenthesis there. Now, if that's what we're going to do, then we should probably say that this is not just 2-bit, but it's U32-bit, which is kind of like overly verbose, but the point is that this exact variable name in this function name is reflected in the code, right? So that's kind of why we do it that way. So let's look at, let's take this and let's do a quick rename. So let's take, let's look for anywhere we see just a bit, and we're going to replace it with this. So find next, and we'll replace. And that was the only place it was called, so that's nice. So that wasn't too hard. And U32-bit, right? We have U32-bit, and that's the exact variable name that is used in the code here, right? So let's look in our shortcuts really quick and see, do we have a U32-bit variable, right? U32-bit. I don't know if we do. Nope, we don't. So U32-bit, U32-bit. We're going to make U32-bit. If we type it correctly, we'll notify that you typed it correctly. So if you type U32-bit, it will surround the word in brackets and put a check mark. Okay, and let's just make sure that if you try to do it backwards, it tells you you did it backwards, and that's not acceptable. So bit U32, and backwards, please use U32-bit. And then we also want like a little definition of like what the fuck does that stand for. So U32-bit means, and U32-bit means, and U32-bit means. Okay, so U32-bit stands for uint 32-bit, right? So bit actually stands for the word bit. That's fine. Okay. So, where are we? Are we good? Are we almost out of here? Like, I really want to be out of here. Okay, so let's analyze this code. Okay, that's good. 1, 2. So this is kind of, this code would happen if we forget to update this value. Like, we add, well, it could happen if we update this value, but we forget to update these. That could happen. But we do need this value, just in case. It's an unhandled case, basically. Okay. There's only one return from here, so there's only one point of return. That's the way I like to keep it. Makes things a lot simpler. Okay, so let's look at where this is called. We have 2 parameters, the tile value and the pixd3d. Tile value, pixd3d. They're gotten from this first parameter here. So that all makes sense. Okay, yeah, we're about ready to just check the syntax, make sure we didn't make any horrible syntax errors, and then we'll save this. We'll save it, and, okay, so we've made a syntax error. Let's just figure out where that is. And once we've solved all of these stupid syntax errors we've made, then we can finally just go to bed, I guess, because I'm getting tired. And okay, let's look at this. So, given, oh yeah, well, that's obviously a problem. So I obviously need to go to bed because that's like a sore thumb. Like, it's like right there. It's very obvious. So dex3d is this guy right here, right? Yeah, so this dex3d. So what we're going to do is, it's a given, so we're just going to plug that in there, right? We're going to be really lazy and just plug it right in there. And, given, right? Okay. Just a little note that this is the given / input value. And that's good for me. I'm satisfied with that. We could also make this a define if we wanted to, but I just don't want to right now. I just want to throw this together, get it working, and then go to bed. Okay, wrong, blah blah blah. 705. Let's take a look at that. Tile value is a U32, and SDF Pro Max is a define, which means that it defaults to an integer or a float, depending on if you added a decimal point or not. So we'll add that there, and that should be good. And let's just give that another run. And do we have a bit shift? Well, let's just paste it and see what happens here. I think for some reason we accidentally did a bit shift here, because I just saw a bit shift. Oh, yeah, so this is, yeah, that, yes, indeed, we had a bit shift, because we didn't comment that out. So let's just make that red. Okay, now that's really obnoxious, so that's good. Now, other people obviously won't see that coloring. That's just a special setting I have in my autocomplete, or not my autocomplete, but the way I did my syntax highlighting, I can color code my comments in certain ways. So let's see what we got here. Assign cannot convert from... we got int and uint. So we're mixing ints and unsigned ints, and that's 712. Yeah, so this is just an annoyance of... GLSL, you just gotta be very explicit. If it's not an int or a float, just be prepared to be as explicit as possible. Okay, so save that, and let's give that a run and see if we can finally get this to just work. Because I'm getting so tired, it's like I'm so close to, like, being able to get this back into a working state, but it's like... I'm just making so many stupid mistakes because I'm tired. 718. So 718. Else. Is this a mistake because do I have a backslash in a oh no, this is oh, I see. Well, you know what? If that's the way we wanna roll if we wanna roll like that, let's roll like that, right? Let's if we want it ugly as hell like that, I mean, it's supposed to be temporary, and it's supposed to stick out like a sore thumb, so that's fine. So the idea is that I want this 9001 to be in line with this comment right here. So that's why I put it between these brackets like this. That's fine. We're intentionally making that as ugly as possible so that it stands out. Okay, what do we got here? It is int and uint. We're mixing that. So 1038. So Control G and go 1038. That's good. We're making progress. We're moving forward. 1038. Yeah, 1, 2, 3. Yeah, that's going to be a problem. We got to have a U32 in front of that. This should already be an unsigned 32 int value. We can just do this if we really want to, just to keep things kind of lined up and nice. And let's take that and try to run with that, see what we get. Okay, it's green. Yay, all right. So nothing should have changed. It should all look exactly the same. It's just that we've stubbed in some of the stuff, right? So we really haven't done much work. We've just gotten everything prepared for doing the next phase of, like, calculating some interior geometry. So let's kind of review what we're gonna do for next time, because I'm tired and I can't think straight anymore. So let's just show you kind of like what we're gonna do next. So tomorrow sometime, maybe at a really odd, inconsistent hour, because I am very tired right now. We're going to take the cross section. So we're gonna take these projections. So we have 2 projections so far. And we're going to take this projection, and we're going to take this projection, and we're going to, let's go to my camera really quick. We're going to take those projections, And hold on, we're going to take those projections and we're going to project them on the X, Y, and Z planes of our voxels. And we're going to use them to Boolean together some very basic geometry, right? So we want to create a shape like this with one of our projections, and then we want to create another projection that is, well, actually, we don't want to create this. We want to create something a little bit thinner like this. And then for another projection, all we want to do is we want to use a projection. We want to take a tile map that's like this, and that just has like a few tiles in the middle, and we want to use that to render a voxel that is mostly empty space, except for there's just a little tiny square inside of it, right? So we're also going to try to render a voxel where most of the voxel is empty space, except for like a tiny like 4x4 section inside of it. So this will be this bounding box is the entire voxel. Most of it's empty space, except for this little piece of geometry in here, which is going to be created by taking this tile map that only has 2x2 pixels in the very center of it, and we'll take this tile map and we'll project it on the Y plane, the X plane, and the Z plane, right? So this is, because this is normal to Z, this is normal to Y, and this is normal to X. And I may have the X and Y kind of flopped here, but the Z I definitely have correct, because Z is the strata, is the different layers of tile maps. But the X and Y I may have flipped in this diagram. It may be the other way around, but the basic idea is still the same. Okay, so that kind of wraps that up. I'm going to name all of my files and go to bed. Yeah, because I'm tired. So yeah, later.